I was trying to show the conversion of malonic esters or acetoacetic esters to corresponding ketones or aldehydes. There are two common methods. First one, they usually use sodium hydroxide followed by acid hydrolysis, sulfuric acid hydrolysis and heat. And then the second one is just using only sulfuric acid and heat. Just trying to show the mechanism for each of them. They are very similar. So I drew the mechanism for the first one. In the first instance, so they are using sodium hydroxide. The hydroxide will attack this carbonyl right here, followed by elimination of an acetoacetic good living group to form this intermediate with carboxylic functional group or with carboxylic acid functional group. This is a basic medium, so the acetoacetic base will grab this proton from here to form the carboxylate ion, and then addition of excess sulfuric acid will protonate every trace of base that is present. So the carboxylate ion will grab a proton from a hydroxonium ion or H+ or an acid to form the final carboxylic acid intermediate that we are looking for. So this is where it starts. This intermediate will undergo intramolecular decarboxylation reaction, where bonds or bonding electrons that are broken are shifted here, and then this bond breaks and the electrons are pushed onto this bond, and then these bonding electrons here will grab this proton from here. And this is a concerted process, intramolecular reaction that is very fast. So this will lead to the formation of the enol that you're looking for. And then carbon dioxide is eliminated, CO2. Now the enol will tautomerize and give us a ketone. Okay. So you can just stop right here, since we've shown the formation of the enol. You can stop right here. Now I went further to show the simple mechanism of how the tautomerization occurs. Basically, the electrons on the oxygen shift towards this bond, and then the double bond will grab a proton from hydroxonium ion to form this intermediate. Now This has a positive charge on oxygen, so water will grab this proton, then the bonding electrons are dumped onto this oxygen to neutralize the positive charge. And here we have a ketone or aldehyde as our final compound. So that's basically how the ketone-enol tautomerization occurs. This is an equilibrium reaction. This is one molecule that is breaking into two. The reaction is driven forward by thermodynamic entropic gain. So this is going to form the enol, and the carbon dioxide is highly entropic process that drives the reaction forward. Yep, so fast intramolecular reaction followed by the entropic gain. This is very fast, and this can occur without protic or ionic medium, or it can occur in a non-protic or non-ionic medium to form the enol and carbon dioxide elimination. So that's how this occurs. Okay, the other mechanism is using sulfuric acid alone. So this is very easy. What happens is this sulfuric acid will protonate one of the oxygens, preferably this one. Okay, that will enable this positive charge to come on this oxygen. Okay, and then water will attack this carbonyl group, and electrons will shift to neutralize the positive charge on oxygen and form this intermediate where this oxygen now has a positive charge. So the conjugate base of the sulfuric acid will grab this proton, the electrons will shift to neutralize the positive charge on oxygen and form this intermediate. Okay, now again electrons are going to shift to eliminate this acetoacetic good living group to form this with a positive charge on this carbonyl, and then this acetoacetic base will grab this proton, and then the electrons will be dumped onto this oxygen to neutralize the positive charge and form our carboxylic acid intermediate to undergo intramolecular decarboxylation reaction, where bonds or bonding electrons that are broken are shifted here, and then this bond breaks and the electrons are pushed onto this bond, and then these bonding electrons here will grab this proton from here, And this is a concerted process, intramolecular reaction that is very fast. So this will lead to the formation of the enol that you're looking for. And then carbon dioxide is eliminated, CO2. Now the enol will tautomerize and give us a ketone. Okay. So you can just stop right here, since we've shown the formation of the enol. You can stop right here. Now I went further to show the simple mechanism of how the tautomerization occurs. Basically, the electrons on the oxygen shift towards this bond, and then the double bond will grab a proton from hydroxonium ion to form this intermediate. Now, this has a positive charge on oxygen, so water will grab this proton, and the bonding electrons are dumped onto this oxygen to neutralize the positive charge. And here we have our ketone or aldehyde as our final compound. So that's basically how the keto-enol tautomerization occurs. This is an equilibrium reaction. Okay. I was trying to explain the equilibrium drive from the enol to the carbonyl. Over here, the double bond is largely in between this carbon and this carbon. But if you look here, you see that the double bond is between an oxygen and a carbon. Okay, this gives us an advantage because this is an sp2 bond. Therefore, the bond between an oxygen and a carbon is much shorter since oxygen is more electronegative, so the bonding electrons are shifted more towards oxygen. This shortness of this bond gives this structure much more rigidity and stability compared to here where this looks more like a single bond and therefore has more vibrations and less rigidity and therefore less stability. So that's basically why the carbonyl has more advantage over the enol. Now, the instance where the enol has the equilibrium is when this R group is double bond conjugated to this double bond. That gives the system more stability because of the conjugated double bonds. Because if you convert this into the carbonyl, then you are breaking the conjugation. So the system will stay more in the enol form. That is that.